Hi guys, Sauce here. This is a pre-calculus content lesson on continuous compounding. Now, previously we were introduced to the special number e. Continuous compounding is going to be an application of using the natural log base or the power base e, this very special number. Let's begin with reminding ourselves about what it means to compound, how money can grow in a bank. We have an equation. A is equal to P times 1 plus R divided by N all to the NT. This is a general equation for compounding. A stands for an amount. It could be an amount of money because we usually use compounding in the context of banking and money growth and money investment. P would be the principal or starting amount of money. R is an interest rate. N is the number of times that we compound. That's the number of times that we apply the interest rate in an interval of time, where T represents a time. Let's give an example of this to make some sense of it. So we could use this formula to calculate an amount of money. That will be our unknown. Let's imagine that we give a bank a principal of $1,000. P's value is 1,000, the beginning amount, times 1 plus, we're going to invent an interest rate. I'm going to invent the interest rate 6%, and we don't, of course, use percents directly in equations. We have to convert them to their decimal equivalent. So 6% I'm representing as 0.06. And the number of compoundings will be 12 times per year. So N, the value, the number of times we're going to compound per time period is 12. That's like compounding once a month, something that used to be fairly standard decades ago when you gave money to a bank. And then we'll raise this to N, again, is 12, and T, let's invent, for simplicity's sake, the value of T is 1, standing for 1 year. Again, N is used twice, and in this example, we're using 12 to be the number of compoundings per time period. If the time period is in years, then this would be 12 times per year, once per month. So we have a formula now for the amount of money that the $1,000 will grow to become in 1 year. And a calculator will show that that amount, 0.06, which, let me make a note, is equivalent to 6%. I put into a calculator, and I've already done this, 0.06 divided by 12, then add 1, then raise it to the 12 times 1 power, and then finally multiply by 1,000, will give us $1,061.68. Now, I've already done this calculation on the side, and the decimal keeps going. I've rounded it to the nearest cent. This is a context of money, so it's natural to round it to the nearest tenth. Notice that 6% of 1,000 would be $60. But because of the compoundings, the fact that we compounded 12 times and applied that interest rate 12 times over the course of the year, that we got a little bit more than $60. $60 would be 6% of the $1,000 if we calculate it in a manner called simple interest. This is compound interest, and we got $1.68 more for compounding 12 times. Let's do this again with more compoundings. I'm going to use the same principle, $1,000 times 1 plus 0.06 is the decimal equivalent for 6%. That's not changing. But I'm going to compound once a day. And once a day means that in the time period of 1 year, there will be 365 compoundings. n is equal to 365, and I've used it twice in the formula. And t is still 1, representing 1 year. Now again, I used a calculator before taping this lesson, and I put in 0.06 divided by 365, then add 1, then raise it to the 365th, and then multiply by 1,000, and I got the amount of money when I've changed the number of compoundings from 12 to 365. And the amount is $1,061.83. Compare it to 12 compoundings. It's not much more money. It's a few cents more. So we can see that compounding will give us more money than simple interest. But the more times we compound per time period, we get diminishing returns. Now, we haven't yet done calculus yet. We haven't used this special number e. We're about to. And we're going to use it when we consider the number of compoundings being infinite. So we're going to create a new formula. We're going to start with the old one here for n number of compoundings, and we're going to draw it just as before. P times 1 plus r divided by n to the n times t. But I've left some space before this expression because I'm going to use the concept of the limit and take the limit of this expression as n number of compoundings goes to infinity. Now, we can't put infinity in as a number. Infinity is a concept, so we need the limit laws and the ways that we solve and take limits. But to do that, notice that this structure of this equation for compound interest includes the definition of e. So we will recall that this very special number e is equal to and defined as the limit as n goes to infinity of 1 plus 1 over n all to the n from a previous lesson. Take a look at the similarities between the definition of e and this equation for compounding that we're taking the limit of. Both are infinite limits. Both have inside parentheses a 1 plus something over n, and both are being raised to the nth power. Now the compound equation has a principal, and it has an interest rate, and it has a time period included in it. So we're going to create a new version of the compounding formula, but we're going to replace the structure that is included in e with e. The principal remains a part of our formula. E is going to take the place of the limit, the 1 plus something over n, and this n in the exponent. All of that gets replaced by e. And what remains is time in the exponent position. And for algebraic reasons that I'm not going to show in this lesson, the interest rate is also a part of the exponent. Look what happened. We took the compound interest formula, wanting to take an infinite limit as the number of compoundings n goes to infinity. We used what e is defined as to replace part of that structure, which gave us a new formula. And this new formula will calculate the amount of money that you have left, or you have, when a principal grows an infinite number of times during that time period. So let's use it and see what happens in the context of an example. Let's take from our previous work the same numbers. Let's imagine that we're trying to calculate, or we want to calculate, how much $1,000 is going to grow when we have an interest rate of 6%, which is 0.06 as a decimal, for 1 year. I've replaced the principal with 1,000, interest rate with 0.06, and t with 1, just like the previous example. But what this is going to calculate now is the amount of money after a year with an infinite number of compoundings. I've done that calculation on a calculator. I put in 0.06 times 1, and then I raised that to that was e raised to that result, and then I multiplied by 1,000, and a calculator gave me $1,061.84. Let's compare it to our previous results. Notice that if I compound every single day, that's 365 times, I only get one less penny than compounding an infinite number of times. That really shows you the diminishing returns the more you compound. Of course, it's better to compound continuously or instantaneously if you want to maximize your money. But you won't get an infinite amount of money this way.